Good evening, Mr. Soumyendu.
Good evening, sir. I was just
So,
waiting for you for this last class.
yeah,
Yeah, I was just waiting. That is 4:59. Saying that you have not joined till now.
yeah, I have joined. I was little late.
Okay,
So,
no. It's okay, sir.
should I proceed with the class?
Yes, sir. You can start. Okay, no problem. You can
All
start.
right, all right.
Thank you, sir.
So, this is module number 4 of IK's class, and this is all about the mathematics. So, as because it is about Indian knowledge system, so I will strictly confine my class, this class, according to your syllabus, and I'll be confined it within the ancient time frame. Although the Indian mathematics ranges from the Vedic texts to the period of Ramanujan, which is the 19th century, but I'll be confined my class, this syllabus, within ancient times, which is from the in 1500 BCE till 1300 CE. That within that period, I'll be talking about the Indian mathematics. All right. So without wasting any time, let me share the screen. Let me share the PowerPoint presentation with you. Is it visible?
Yes, sir. It is visible. It is clear.
Okay. Thank you. So, mathematics on Indian subcontinent has a long and rich history of more than 5,000 years. It developed much earlier than in Europe and influenced regions such as China, Southeast Asia, Central Asia, and Europe. Indian mathematicians made important contributions to many areas, including geometry, arithmetic, binary numbers, negative numbers, algebra, trigonometry, and early forms of calculus. One of their greatest achievements was of the development of decimal place value system, which is still used all over the world today. Now, for a long time, many European mathematicians did not accept negative numbers and even zero as meaningful concepts. They considered these ideas to be illogical. This delayed the progress of mathematics in Europe for many years. Although Indian mathematicians has often been underestimated because of their Eurocentric views, but the Indian subcontinent continues to have strong mathematical traditions from the Vedic period, which is around from 1500 BCE to the work of Srinivasa Ramanujan in the 20th century. As I already said, that I will confine my, although it is stretched to the contribution of Indian mathematics can be talked about, can be stretched to Ramanujan's period, but I'll be talking till the 13th century here. In India, mathematics is known as Ganita and has always been an important part of daily and intellectual life. From ancient times, people developed mathematical methods to solve practical problems. One of the Vedangas, named Jyotisha, used mathematical ideas to study the movement of planets and stars. Another Vedanga, Kalpa, applied geometry to build Vedic altars in different shapes. Buddhist and Jain scholars also studied mathematics deeply and wrote important books on the subject. I'll be discussing about all these things later on. Then what began as a practical need in early times continued as an unbroken tradition through later periods. Over the centuries, Indian mathematicians made valuable contributions to almost every major branch of mathematics. These include algebra, geometry, trigonometry, intermediate equations, squares and cube roots, permutations and combinations, numerical methods, approximation techniques, infinite series, and many other fields. All right. Now coming to the second point of your syllabus, which is the unique aspects of Indian mathematics. So the one of the most distinctive feature of Indian mathematics is its close connection with poetry, literature, and philosophy. Mathematical ideas were often expressed in the form of sutras and verses. These verses were easy to memorize and helped in perceiving knowledge through oral tradition. Works such as Aryabhatiya, Lilavati, and Bijganita present complex mathematical ideas in poetic language. This blending of logic, creativity, and literary beauty make mathematics accessible and enjoyable, reducing fear and stress among the learners. So this is the first unique aspect of the Indian mathematics. The second unique aspect is the mathematics were taken as a part of daily life. So in ancient India, mathematics was not confined to scholars only. It was applied in temple architecture, trade and commerce, astrology and astronomy, ritual and altar constructions, other constructions, building constructions, land measurement, etc. For example, the constructions of Vedic altars required precise geometrical knowledge. Similarly, merchants also used advanced arithmetic for calculations. Thus, mathematics was deeply connected with practical life. This is the second unique aspects of the Indian mathematics. Now, the third aspect was the use of mnemonics. Indian mathematicians use short verses and sutras to convey complex rules and formulas. These acted as mnemonics devices, helping students remember procedures easily. For instance, Aryabhatta represents his sine table and astronomical calculations through brief poetic verses. These methods improved memory, understanding, and transmission of knowledge across generations. The fourth point is algorithmic and procedural approach. Another unique feature is the emphasis on algorithms, step by step procedures to solve problems. Indian mathematicians focused on more on how to solve problem rather than only proving. Example include algorithms for square and cube roots, methods for solving intermediate equations, techniques for series and approximations. This constructive approach resembles modern computational thinking. Now, Indian mathematics developed continuously from the Vedic period, as I said, to the early medieval period. Early medieval period is 1300, considered to be 1300 CE, without major interruptions. Contributions come from various regions of India, starting from Gandhara. Gandhara is modern day Afghanistan region. So from Gandhara, Kashmir, Gujarat, Bengal, and many regions from South India, all the mathematicians and scholars have contributed in Indian mathematics. So this geographical spread shows that mathematical learning was widespread and institutionalized in ancient India. Now, Indian mathematicians introduced many fundamental ideas much earlier than the other civilization. This is another very important unique aspect of Indian mathematics. What are these fundamental ideas? Like the zero as number, decimal place value system, negative numbers, infinite series, trigonometric functions, and approximation of pi. These innovations later influenced Arab and European mathematicians. And listening only instead of listening only the instead of focusing only into the exact values, Indian mathematicians developed methods for approximations suited to practical needs. This is very important and very interesting also. For example, several approximations of square root and pi were developed from Vedic times to Bhaskaracharya's second period, which is 1500 BC to 12th century CE. These shows their scientific attitude and concern for real world applications. So these are the some of the unique aspects of Indian mathematics. Now coming to the third point, which is the Indian mathematicians and their contributions. So it has a very huge list. I have, for easy understanding, I have divided this thing into a chart for the better understanding. You can have a snapshot of this slide, and it will be easy for you to memorize. So Indian mathematics is distinguished by its integration with culture, practical life, literature, and philosophy, as I said. Use of sutras, algorithm methods, and approximation reflects a scientific and holistic outlook. The uninterrupted tradition from Vedic times to early medieval period uh, produced remarkable scholars who contributed to arithmetic, algebra, geometry, trigonometry, calculus, and number theory. The first text which we have to talk about, we had to, we have to must recite, which is Vedic text. It is the Vedas are dated from at 1500 BCE. This is the earliest dating can be found, and in these Vedic texts we find earliest mathematical knowledge, number system, Pythagorean triplets, decimal naming system, concept of infinity. These kind of ideas were talked about in the Vedic text. Then Lagadhas composed a text called Vedanga Jyotisha in 1300 BCE, where he talked about astronomical models, movements of sun and moon, equinoxes and solstices. Then Bodhana, Apustambho, Katyayana, and Manava, they all contributed to a book called Shulva Shastras. This Shulva Shastra is dated to 800 to 600 BCE, where we find the concept of early geometry, square root and pi approximation, construction of squares, rectangles, and trapezia. Then Panini's Ashtadhyayi in the 500 BCE, composed in the Khyber region, talked about algorithmic rules, context-sensitive grammar and arrays, inheritance, polymorphism, and BNF system. Pingala's Chandrashastra, written in circa 300 BCE, also talked about no it talks about the some completely new idea. It talked about the binary system and Meru Prastara is known as Pascal's triangle. Then it also talked about power algorithms and zero as symbol. Buddhist mathematical works dated from 500 BCE to 500 CE talked about various aspects such as multi-valued logic, intermediate numbers, and infinite numbers. There are also Jaina mathematical works, which includes Surya Pragrapti, Jambudvipa Pragrapti, Bhagavati Sutra, Stananga Sutra, Uttaradhyayan Sutra, Tilayapannati, and Anujogadhara Sutra. These texts were composed between 200 to 300 CE. So these are the texts which talked about large number powers, logarithms, arc of cycle, combinatorics, mensuration, decimal system, and also it talked about the approximation of pi. Then the famous mathematician Aryabhatta, who composed his book Aryabhatiyam in Kusumpur of Bihar during 476 to 550 CE. He in this book he talked about roots, place value system, sine tables, quadratic equations, intermediate equations, trigonometry, and astronomy. Varahamihir composed 3 books, namely Brihat Samhita, Brihat Jataka, and Pancha Siddhantika. He composed these books in the Ujjain region, which is the Madhya Pradesh region, dated 482 to 565 CE, where he talked about trigonometry, combinatorics, magic squares, summary of five Siddhantas. Bhaskaracharya one wrote a commentary on Aryabhatiyam. Apart from that, Bhaskaracharya also composed two other books, which is called Laghu Bhaskaryam and Mahabhaskaryam. He composed these books in the Gujarat region of Saurashtra, dated 600 to 680 CE. In these books, he talked about sign approximation, intermediate equations, and planetary astronomy. Brahmagupta composed three books. One is uh, uh, no, Brahmagupta composed two books regarding mathematics. One is Brahmasputa Siddhanta and Khanda Khadaka. He composed these books in the Villamal region of Rajasthan, dated 598 to 668 CE. In these books, he talked about zero as and negative numbers, algebra, linear and quadratic equations, a cyclic quadrilateral formula. Then Birhank composed Bihad Jati Samuchaya, a text which is written in Prakrit. It is composed in the 600 CE. It talked about Fibonacci numbers, Prodeci, and poetic meters. Sridharacharya composed two books, which is named as Trishatika and Patiganit. Sridharacharya was a person from West Bengal in Hooghly district, and he composed this book during 870 to 930 CE, where in these books he talked about algebra, quadrilateral equations, square root approximation, and commercial mathematics. Then Mahaviracharya composed a book called Ganita Shara Samgraha. He composed these books in Gulbarga region of Karnataka during 800 to 870 CE. It is a comprehensive textbook of mathematics discussing about arithmetic, algebra, series, permutations, and combinations. Jayadeva composed his mathematical idea during the 10th century CE or earlier, where he talked about cyclic method, which is known as Chakravala second order intermediate equations. Sripati composed three books. He is from the Maharashtra region, dated 1019 to 1066 CE. His book are named as Sripati, Ganita Tilak. Sripati's books are named as Ganita Tilak, Siddhanta Sekhara, and Dhikoti Dhikaran. So there are three books. Again, I'm taking the names: Ganita Tilak, Siddhanta Sekhara, and Dhikoti Dhikaran. These are composed in the Maharashtra region, as I said, and these books are talked about mathematical astronomy, planetary calculations. Whereas Bhaskaracharya too composed books named as Lilavati, Bij Ganita, Siddhanta Shiramani, and Bashona Bhashya. He composed these books in the Karnataka region during 1114 to 1185 CE, where he talked about proofs which is known as Upapatti, algebra, trigonometry, calculus ideas, astronomy, stars, and many more. So from Vedic times to Bodhayana and Aryabhatta to second Bhaskaracharya, Indian mathematicians made pioneering discoveries that shaped global mathematics. Their legacy continues to inspire scholars today and remains a vital part of the world's intellectual heritage. Now, coming to the next point, which is algebra. So, algebraic concepts can be found in ancient Indian texts such as the Shulbha Shastras, which date back to 800 BCE. These texts contain methods for solving linear and quadratic equations and provide geometric constructions related to algebraic principles. Brahmagupta, an influential mathematician of ancient India, made significant contributions to algebra in his work called Brahmasputa Siddhanta. He introduced the concept of zero and provided rules for arithmetic operations involving zero. Brahmagupta also developed methods for solving quadratic equations and intermediate equations. Indian mathematicians developed various algebraic techniques for solving polynomial equations and manipulating algebraic expressions. These techniques include methods of factorization, expansion, and solution of polynomial equations of higher degrees. Bhaskaracharya too is another notable mathematician contributed to algebra in his work Siddhanta Shiromani. He provided solutions for intermediate equations and developed algorithms for arithmetic operations involving fractions and irrational numbers. Algebra was closely integrated with other branches of mathematics and applied in fields such as astronomy, architecture, and commerce. Algebraic techniques were used in astronomical calculations, geometric constructions, and financial transactions, demonstrating the versatility and practical utility of algebra in diverse contexts. Now, the fifth point, according to your syllabus, is geometry. So, in geometry in India traces its origin to ancient times with geometric principles and constructions found in the texts such as the Vedas and Shulva Sutras. The Shulva Sutras contain instructions for constructing altars and fire pits using geometric methods, demonstrating early applications of geometry in religious rituals and architectural practices. Indian mathematicians excelled in geometric constructions, particularly in the context of architectural and ritualistic practices. The Shulva Sutra provide detailed instructions for constructing geometric shapes such as squares, rectangles, and circles, as well as more complex geometrical structures used in sacrificial rituals. Geometry played a crucial role in Indian astronomy as well, where precise geometric models were used to study celestial phenomena and calculate planetary positions. Astronomical texts such as the Siddhanta Shiromani of Bhaskaracharya II contain geometric models for explaining planetary position, eclipses, and other astronomical phenomena. The Indian mathematicians developed various geometric concepts and theorems, including properties of triangles, quadrilaterals, circles, and polygons. Notable geometric results include the Pythagorean theorem known as the Sulvashara theorem, also, which predates the appearance in Greek mathematics. Geometry found expression in Indian art and architecture, where uh, intricate geometric patterns and designs adorned temples, sculptures, and monuments. Geometric motifs such as the mandala and the yantra were used in religious art and symbolic representations and in tantra. Geometry was closely integrated with other branches of knowledge, including mathematics, astronomy, and philosophy. Geometric principles were applied in diverse fields such as medicine, music, and linguistics, reflecting the interdisciplinary nature of Indian intellectual traditions. Now, coming to the sixth point, which is trigonometry. Trigonometric concepts can be date back to the ancient texts such as the Vedas and the Sulva Sutras as well, which contain geometric principles and measurements related to altars and fire pits used in the Vedic rituals. So those things also involve geometry and trigonometry both. So these texts, the Vedas and the Shulva Sutras, demonstrate early applications of trigonometric ideas in practical geometry. Trigonometry played a crucial role in Indian astronomy, where precise trigonometric calculations were used to study celestial phenomena, predict planetary positions, and determine the timing of eclipses. Astronomical discourses such as the Surya Siddhanta and Siddhanta Shiromani contain extensive trigonometric tables and methods for spiral trigonometry. Indian mathematicians introduced trigonometric functions such as Jaya, Kojaya, and Utkarmajaya, which is known as sine, cosine, and versine, to describe relationships between angles and sides in the right angle triangles. These functions were used both in plane and spiral trigonometry to solve geometric and astronomical problems. Indian mathematicians produced numerous trigonometric identities and formulas which include relationship between trigonometric ratios as well as series expansions and integral expansions of trigonometric functions. Trigonometry found practical applications in architectural design, where precise geometric measurements and proportions were essential for constructing temples, monuments, and other structures. Geometric principles such as the golden ratio and geometric motifs such as mandalas were used in religious art and architectural ornamentation, which was impossible without the knowledge of trigonometry. So these are the algebra, geometry, and trigonometry. Now coming to the seventh point, which is the binary mathematics and combinational problems in Chanda. So in the Chanda Shastra, uh, Chanda Shastra, an ancient Indian discourse on Sanskrit Prodese attributed to Pingala, there are elements that anticipate binary mathematics and combinational problems. While the primary focus of the Chanda Shastra is on poetic meter, it contains mathematical concepts and techniques that are foundational to modern mathematics. Pingala represents poetic meters called chandas using binary notation. He, describe, he describes various types of meters as sequences of short and long syllables. Short syllables were called laghu and the long syllables were called guru, denoted by binary digits 0 and 1 respectively. So the short syllables were denoted as 0 and the long syllables were denoted as 1. These binary representations allow for the systematic analysis and generation of different numbers, resembling the binary representation of various numbers. Pingala discusses combinational problems related to the enumeration of meters with a given number of syllables and a fixed total duration. He presents recursive algorithms for containing the number of possible meters, which involve the manipulation of binary sequences. These algorithms anticipate modern combinational techniques enumerating combinations and permutations. Chandashastra contains a famous problem known as Meru Prastara, which involves constructing a staircase like arrangement of syllables with a prescribed total length. The solution of this problem yields a sequence of numbers that resembles the Fibonacci sequence, demonstrating early insights into recursive patterns and mathematical sequences. Pingala's work exhibits a mathematical structure based on binary sequences and combinational principles. He discusses concepts such as symmetry, repetition, and transformation, which are fundamental to modern mathematical analysis and combinatories. While the Chanda Shastra predates the formalization of binary mathematics and combinational theory in modern mathematics, but it proves valuable insights into but it provides valuable insights into the mathematical thinking of ancient Indian scholars. Pingala's use of binary notation and combinational techniques in the context of poetic meter demonstrates the sophistication and depth of mathematical knowledge in ancient India, laying the foundation of subsequent developments in mathematics and computer science. Now, the eighth point after this would be the magic squares in India. So, a magic square is a square grid filled with distinct numbers where the sum of the number in each row, column, and diagonal is the same. So here is the picture. You can see this picture. The picture on your right is taken from the Parshvanath Jain temple from Khajuraho, dated 10th century CE. It is showing a magic square called Chautisa. So if you add the numbers in each row, column, or diagonal, you will have you will have the number 34. So this is the example of magic square. So these magic squares are method in ancient Indian texts. This is mentioned in the ancient texts such as Vedas and Puranas, where they are associated with mystical and religious significance. The earliest known reference to magic squares in Indian literature dates back to 200 BCE in the text called Krishna Yamala. It is a tantric text. Krishna Yamala. Indian mathematics, Indian mathematicians explored magic squares in depth in their mathematical discourses. The great mathematicians Aryabhatta described magic squares in his work Aryabhatiya, where he discussed various properties and constructions of magic squares. Indian mathematicians classified magic squares based on their order, the number of cells along each side, and studied their properties systematically. They developed algorithms for constructing magic squares of different orders and explored patterns and relationships among different types of magic squares. In Indian culture, magic squares are associated with symbolism and ritualistic principles. They are sometimes used in religious ceremonies, architectural designs, and talismanic objects where they are believed to possess mystical powers and bring good fortune. Magic squares were integrated into various intellectual domains, including astrology, astronomy, and numerology. Indian astrologers and astronomers used magic squares as a tool for deviation and prediction, associating specific magic squares with planetary influences and cosmic energies. Overall, magic squares in India reflect a deep appreciation for mathematical patterns, symbolic representations, and cultural symbolism. Through their exploration of magic squares, Indian mathematicians contributed to the broader understanding of combinational mathematics, symmetry, and numerical symbolism, leaving a lasting legacy in the history of mathematics and culture. Now, coming to the conclusion. In conclusion, the study of Indian mathematics reveals a rich, continuous, and highly developed intellectual tradition that spans several millennia. From the Vedic period to the early medieval period, Indian scholars made remarkable contributions to almost every major branch of mathematics, including algebra, geometry, trigonometry, combinatorics, and number theory. The close integration of mathematics with literature, philosophy, daily life, and practical needs reflects a holistic and scientific outlook that distinguished the Indian mathematical thought. Innovations such as the concept of zero, the decimal place value system, advanced algorithms, approximation methods, and infinite series laid strong foundation for global mathematical development. Despite historical neglect due to Eurocentric perspective, the enduring legacy of Indian mathematics continues to inspire modern scholarship and remains an essential part of the world's intellectual heritage. So, with these words, I am ending my class here today. I have tried to explain all the relevant points according to the syllabus in a simple manner possible. Now, if you go through the provided study materials, I hope you will able to comprehend the topic very easily. Thank you. Thank you for listening. Back to you, Soumyendu sir.
So is there a problem?
No, I have finished my class actually.
Oh, acha. So today you have completed within that. Okay, okay, sir. Okay, okay.
Yeah, I
Yes.
because I have যেটা করেছি আমি সেটা হচ্ছে আমি আমি জিনিসটা চার্ট করে বুঝিয়েছি, তার জন্য খুব সহজে জিনিসটা হয়ে গেছে।
ও আচ্ছা আচ্ছা, ঠিক আছে স্যার, তাহলে আমি তাহলে ক্লোজ করে দিচ্ছি আমি।
ওকে, ওকে,
ওকে,
ওকে,
থ্যাংক ইউ।
ওকে, থ্যাংক ইউ।